Liquids and Solids Review, focusing on IMFs. So when we take a look at a molecule, there are attractive forces that are occurring. And there are two attractive forces in this chapter that are extremely important to be focusing on. There is the bond or attraction that is happening within the molecule, and then there's an attractive force that's happening between the molecules. Between the molecules are called intermolecular forces. Within the molecule is called an intramolecular force. The intra is much stronger than the inter. In most cases, when we are dealing with topics in this chapter, we are looking more at the intermolecular forces, because the intermolecular forces are being overcome in phase changes, for example, from a solid to a liquid to a gas. We are not changing the compound. We are simply adding or removing energy by overcoming those attractive forces. I like to think of them as the stickiness between them. So here are some of the forces that we are looking at. Obviously, there are more than these, and we could break them all down, but these are the ones that we're going to run into the most, especially in AP chemistry. So the way that I look at this is that usually you kind of have a separation. Above the line, you have ionic, which is going to be extremely strong due to the fact that there's an attraction between a fully positively charged ion and a negatively charged ion. So that is a really strong attractive force. The other three are usually occurring in a covalent compound, which is a compound that is sharing electrons. So when I look at these three, this is what I try to focus on. I ask first, is this polar or is it nonpolar? So today, whenever we address one or the other, if it's a polar compound, then we have to ask ourselves, is there H bonding? Or is it just simply polar? If it's nonpolar, then there's only London dispersion forces. To be clear, for H bonding, that's with F, O, or N, and H. You need to have FON with your H bonding. So let's take a look at a couple different questions and problems that could arise when dealing with IMFs. Here are two scenarios of this or that. So the first one, I want to know which one has the lower boiling point. And the second one, I want to know which one has the higher freezing point. So two pretty straightforward questions. So usually an answer for something like this would require probably two sentences. One would be to identify what type of IMF is in each one, and then to simply relate it to the scenario that is happening. So you could be talking about viscosity or vapor pressure or volatility or fill in the blank. It still all applies to the IMFs that we are dealing with. So the first thing is you need to make sure that you're understanding what the scenario is. So let's talk about the first one here. I have lower boiling point. So that means, first off, a boiling point, you are boiling, so you are going from a liquid to a gas, okay? So you need to put energy into that compound to overcome that attractive force to go from that liquid state, which is heavily attracted to each other, to a gaseous state, which means that the kinetic energy is much greater than the attractive force between the molecules. So the next step you need to do is get your mind set on what does it mean to be a lower boiling point. Is that a stronger or a weaker IMF? That has to happen before you can move forward. So if it's a lower boiling point, it doesn't need as much energy to overcome those attractive forces. So if it doesn't take as much energy, that means those forces are not as strong. So I am looking for the weaker IMF. Okay, so I'd like you to pause the video right now and identify what IMFs are present between each molecule, and then which one would apply to having the lower boiling point. I think the most important thing to do is to draw these out. So if I take methanol, it would look something like this. And water is a bent molecule. And that is important. If it was linear, that changes what I'm dealing with. Then it might go from polar to nonpolar. So your job is to identify the parts of these molecules and what's happening in here. Okay, so let's take a look at the methanol first. Right here, this is definitely H bonding. That's an H bond. All of this is, for all intensive purposes, an LD. So half of this is very polar and the other half is very nonpolar. Over here, we basically have two H bonds, right? This is an extremely strong dipole, which is what an H bond is. It's a really strong dipole. So right there answers the question for me, is that this is the really strong IMF and this is the really weak IMF in comparison. So if I'm now going back to my initial question, I kept my mind straight by saying what I'm looking for. I'm looking for the lower IMF. So the answer would be the methanol. Now pause the video again and start from scratch without any assistance. You are looking for the higher freezing point between propane and phosphorus trihydride. Sometimes this is harder for students to comprehend with freezing points. So let's first make sure that our brains are aligned. Freezing point means I'm going from a liquid to a solid, meaning that the amount of energy I take out, eventually the attractive forces will allow them to stick together, and those attractive forces will actually overcome or be stronger than the kinetic energy that the molecule actually has. So if it's a higher freezing point, what that means is that you have it at a higher temperature, meaning that you have more energy in the molecule, yet they still stick together. Higher energy in the molecule, but they still stick together, meaning that they are stickier. So what we're looking for is a greater IMF, because those IMFs will be strong enough to be attracted to another molecule and not be broken by the overall kinetic energy. So right there, a lot of you probably can answer this question at this point. But these are going to be London dispersion forces, and this one's going to be dipole-dipole. And if we just break that down for one moment, we can see the drawings of the two. Is that the propane, simply put, will be a nonpolar structure, and the pH3, because of the lone pair pushing down the other hydrogen molecules, it creates a net dipole moment. So that's polar. So that has the stronger IMF. So that's why that one would have the higher freezing point. This next question gives students a lot of challenges. Whenever we start talking about volatility or vapor pressure, it becomes very confusing. So here's a statement. Q is more volatile than J, whatever those are. Purposely using Q and J so you can't actually analyze what that would be. So let's just take a look for a second. When I say volatile, it also relates a lot to vapor pressure. It's easily, or it can easily evaporate, or evaporates easier than another structure or substance. So what we have here, this picture helps illustrate this, is you can kind of think of two forces acting on each other. So you have the atmospheric pressure, and you have the vapor pressure. And those two are going to butt heads. The vapor pressure has to equal or be greater than the atmospheric pressure to be able to begin boiling. Any molecule, if it gains enough energy, can overcome the atmospheric pressure. That's just called evaporation. Everything will slowly evaporate, but a volatile substance will evaporate very quickly because the IMFs are very low. So let's discuss that quickly. So when we say something is more volatile or not, let's talk about it in terms of just IMFs. If you have a greater IMF of anything, what that means is you have, I think of it as being very sticky. So what does that mean? Well, if we take a look at this structure right here, the forces between them is very, very strong. Okay, that would mean that I have a very high IMF, very strong IMF. If they're very weak, then they're not as sticky. So if you're really attracted to each other, it's really hard to break apart. So here's the one IMF relationship that doesn't quite relate as well, and that's with vapor pressure. So the stronger the IMF, usually the lower the vapor pressure, meaning that it can escape easily. It does not, it's able to jump away very easily. So when you say something is very sticky, my best statement I would say is it does not easily, and we'll kind of break it down to this, jump to a gas. Okay, so all that being said, trying to get our minds in the right track is that if Q is more volatile than J, that means Q has the lower IMF and J has the stronger IMF. Again, it is so vital and so important that we establish which ones have the stronger IMFs before we jump into our problems. So take a moment, and I'd like you to answer each of these. Which one has, oh, I'm sorry. Let's establish this. Which one has the lower boiling point? Which one has the higher vapor pressure? And which one has the greater viscosity? So let's establish those as our norms. I'd like you to identify, is it Q or J? And then a single sentence explaining why. If you want a lower boiling point, Q would be the answer, because with a lower IMF, it requires less energy to go from a liquid to a gas. You would be able to overcome those attractive forces easier and break those forces to be able to become a gas with less energy. For a greater vapor pressure, it would also be Q, because if Q is more volatile, then it also has a higher vapor pressure. They're basically synonyms, but with a lower IMF, the molecules are not as attracted to each other. So again, they are able to escape and become a gas easier. So they create a greater vapor pressure, greater pressure on the surface of the liquid because of that lower IMF. And lastly, viscosity. If you want a greater viscosity, that means that a BB or whatever would flow through it. It would take longer. It would be thicker. The liquid would be thicker. J would be the higher viscous compound, because with a higher IMF, I would have a stronger attractive force. It would cause the flow rate to be slower, which would mean it's thicker due to the stronger attractive forces. So that's some of the information we can get by a simple statement. Again, say this, look at the statement, and then you need to identify what type or comparative IMFs you have. Once you do that, everything else falls into place. This next scenario is an interesting one. Which pair is linked correctly? So it says correct IMF link. Please be aware of the implications of what that means. It means that if one of these compounds, let's just use this for example, is linked to another one of these compounds, right? If HBr is right here linked to another HBr, we're talking about the IMF, this force right there. So which one is the correct IMF link? So let's take a look at each one with my suggestion to you, pausing the video and simply writing underneath, thinking about what would be that IMF. So I will just give you one example quickly, is that if H2 was bonded to through IMF to another H2, so let me actually draw this out. Here's one hydrogen, and it's attracted to another hydrogen molecule. That force right there can be determined by looking at the actual molecule itself. This molecule does not have any polarity. It is not a metal and a nonmetal, so it's not ionic. So to me, this one clearly is an LD. And if it's an LD, that is not matched correctly. That is not H bonding, even though that's a hydrogen. So for the next 5, please think about from one molecule to the other, or just in general, what would be the strongest IMF involved in that, that structure. Complete it, and hopefully a pair is sitting there with a correct match. Understanding molecular geometry is really important. So looking at BlCl3, it is really vital that you understand that it has 3 valence electrons. So I have a structure that looks like this. The minute I see that, I think of that being nonpolar. And if that's nonpolar, that's LD. Okay, that's so important. So if I look at this next one, C2H4, I'm just going to draw each of these ones. So more or less, that's what it would look like. So let's break it down quickly. Covalent bond, what that probably is usually referring to is the actual intramolecular force here or there or wherever you'd like. But that's not what we're talking about here. We're talking about the attraction force in between another ethene, excuse me. So this is another LD. So this one's not right. That one's not right. Ionic. This cannot be ionic. Hydrobromic acid being attracted to another one would be a dipole-dipole. That can't be right. London refers to a nonpolar substance. Because Al does not have a lone pair, this is nonpolar. So this is London. So this should be the right answer. Not to be confused with if you ever got a pH or PCl3, that, because of those lone pairs, would cause it to be a trigonal pyramidal, and that would be polar, so that would be a dipole-dipole, for example. And then lastly, network. Network solid usually refers to a repetitive structure involving usually silicone or carbon. This is not. This is clearly ionic, so that one's not going to work. So there you go, matching the correct IMF with the formula. Let's make a phase diagram. The information on the right is truly all you need to accurately make a phase diagram, which will provide 3 phases. It will provide the proper slopes and angles for the lines. It may not be completely accurate, but it will be a good representation of what is needed. So what is important is that we are labeling the X and the Y axis. So on the Y, we're going to have pressure, and I notice on our information that I was given ATM, and on the bottom, I'm going to do temp, and in this case, it looks like it's Celsius. All right, so it's important to kind of scale this off. Now, I don't know what compound this is at all, but what I have noticed already is there is a repetitiveness. So I want to kind of maybe start there. So I'm going to actually make this around 1. I'm going to go up pretty high here. So I'm going to call this 1. Okay? So what I'm going to do is actually make the lines there. I'm going to make these 2 points right away. I'm going to make my freezing and my boiling points. So again, it does not have to be perfectly to scale, but what I'm going to do is I'm going to make this -20. I'm going to just move my temperature way out here just to get it out of the way. And I'm going to make a point. I'm going to go straight up. And then I'm going to make one at 75. And I just arbitrarily kind of made a separation there. And I make these dotted lines not too dark, but enough to be able to see. So here's one of my points. There's the first point. Here's my second one, right? This is my freezing point. This is my boiling point. Okay, they just line up. Okay. Next, we need to get the critical point. So what we could do is just, it looks like that's the largest temperature, so I'm just going to take that all the way to the end. I'm going to say that's 175. Again, not necessarily to scale. And the ATM is 7.2, so let's just bring that up as high as we can go, or almost as high as we can go. So again, that will be right about here. Again, you can make more dotted lines, but usually the freezing and the boiling point are the ones that we make. Lastly, triple point. Very important where we set that. Okay, so it's vital that you have, and not again to scale, but relative to the other values that you put on the table. So the one I care more about right now is this temperature. The pressure, it's going to be, well, a little less than half. Well, it's also a negative technically. Well, no, shoot, that can't be. That's not there. I apologize. It's at 0.45. I'm going to make this -15. I'm going to make my triple point right about there. Okay, so what you need to understand is from the boiling and freezing point, those lines go to the triple point. The triple point, unfortunately, we don't have any more information right now, so I'm just going to have to kind of take that and bring it to the side. So what I'm going to do right now is go off of this, and then I need this to equal or go through the boiling point and the critical point. Now, this is not the greatest drawing I've ever done, but it'll serve what we need. So a couple things to see. One, if I asked you to label all of the regions, can you do that? Pause the video and label each region and what phase is where. Hopefully you said this is the solid, this is the liquid, and this is the gas. Now, when we're taking a look at that, please understand that all of this is the gas. It's not where the dotted lines are. I mean, sorry, all is the solid, right? All of this is the liquid. And all of this is the gas, technically. All right, what if I pose a couple other questions to you quickly? Here's my first one. Is the solid more dense than the liquid? I have no idea what this substance is, and my graph probably is not drawn perfectly, but I have enough information again to figure this out. Due to the fact that my triple point is further to the right than my solid, it creates the slope of this line, okay, to have a negative slope. Another way to think of it is that this mass of area is sitting over the area of the solid. Either way, however that works, usually the way I see it is you talk about the slope because of the negative slope of the solid to liquid phase boundary, is that you can say is that the liquid is more dense. That is actually quite unusual. Usually the solid is more dense. So what would that have to look like before we move on? What would that have to look like to have a more dense solid? Well, if I just drew a really generic picture, it would have to look like this, where you have your solid, your liquid, and your gas. Now my solid has a positive slope, and that area is sitting above that liquid area, so it's more dense. All right, let me pose one more question. Had 0.3 ATMs and negative 40 degrees Celsius, so that's my point I'm looking at. Starting there, if heat was added, what process would eventually occur? Okay, so what you need to do is first find the place on your table. So it's not going to be exact. It just won't be. But if I'm at negative 40, so that's, let's say, around here, and the pressure is about negative 0.3. Let's say I'm right here. That's about right. I don't know if that's exact, but it's close enough. So this is 0.3. That's at least what I'm establishing, and I'm saying this is negative 40. If heat was added, what process would eventually occur? So what that means is that I'm going to add heat. Temperature is moving from left to right. So eventually I'm going in this direction. When you cross over a threshold, a phase change has occurred. A phase change has occurred. If you're on the line, you're at equilibrium, meaning that you have the same amount each way. You're not sliding one direction or the other. So what is that process? That is sublimation. Correct? Just to do a little contrasting, if I had a point way up top here where the X is, and I said that I reduced temperature, then I could say that condensation would occur. Okay? You can also do it this way, where my other X is. If I instead said I increased the temperature, and I did that, and I asked what process would happen, condensation would also occur that way. Why? Because I'm going from a gas to a liquid. So those are some things that you can do with a phase diagram. Let's take a look at heating curves. Here's the scenario I want to look at. How much energy is absorbed by having 15 grams of ice at negative 5 degrees if it is then brought to 125 degrees? So by having a little knowledge of what a heating curve looks like, it helps a lot. So more or less, what we are doing is that we're starting as a solid, correct? And at this point, because this is water, if it ever says ice, you got to assume water, then I am ending up as a gas. So I'm going through all the phases. So this is the generic heating curve. If you're really accurate, the second plateau is always longer than the first because it takes more energy to overcome the IMFs from a liquid to a gas, because you have to completely break away, versus from a solid to a liquid where you're just causing a little more fluidity instead of being such a rigid solid. So what I'd like to do is we're going to number these only for the sake of helping us recognize what's happening. So those are my 5 different places I need to calculate. They have temperatures associated with them. And honestly, there's only really 2 things that I'm doing. I have given you different constants, either specific heat capacities or enthalpies. So if you really know what you're doing, I'd like you to pause it right now and try to figure all this out. If you need a little help, then let's talk a little bit about the equations, and feel free to pause it at any time as you feel that you need, so you can finish this accurately. So if I look at each portion of my heating curve, I recognize that the odd numbers are all increasing in temperature. Okay, so if we're changing in temperature, we have a certain mass of our substance, and that means that if I'm changing temperature, I have a final temp, so it's final minus initial. So all of these are going to be using Q equals MCAT. Okay. The other one, the plateau, clearly does not change in temp. So that cannot incorporate change in T. So that's where I'm using my change in H. And whenever you're dealing with enthalpy, it matters how much you have, period. That's it. So the amount of energy coming in or going out is dependent on the amount of substance you have. So if I just break this down, I'm only number these based on what I numbered before. So my first part of my heating curve is talking about heating my solid. So this is a solid. Then well, let's just keep it at that first. So this is my solid. So if that's my solid ice, what I have is 15 grams of ice. My specific heat capacity of ice is 2.1 joules per gram Celsius. And my temperature change, I started at -5. I'm ending at 0. You do need to know your phase change values for water. So at this point right here at number 2, I'm going from a solid to a liquid. That's my melting point. And a melting point at water is 0. So this is at 0 degrees. So then this is my my boiling point. I'm going from a liquid to a gas. So that's my boiling point. So for water, that would be 100 degrees. So that would be my first value. I will calculate that in a moment. Then when I have a phase change, all the energy is going into breaking or overcoming those IMFs. So I need to determine how much of my substance I have. So I have 15 grams of water. 1 mole is 18. And in this case, that is vapor enthalpy of fusion. So as you can see, I have 2 different units right now, and that's going to be an issue, but I'm not going to address that until I'm done. So that the formula in red, I'm going to apply to steps 3 and 5, and the process in blue, number 2, I'm going to apply it to step 4. So pause it and try to execute that and work on 3, 4, and 5, and try to add all this up. How much energy does it take to take my ice from -5 degrees to 125 degrees? So taking a look at it, step 3, you take your 15, multiply by whatever's given. Sometimes we have 4.18. In this case, I was just given 4.2 for the specific heat capacity of liquid water. And then it's 100, which is my final, minus 0, which is my initial, because that's the route that I'm taking. Okay. Then step 4 is my phase change. So I put in the 15 and the 18 again, and instead of using 6.02, I use 40.7, and that's the value I get. And then finally, please understand and have knowledge of what you're looking at. You are ending at whatever value you're given, which is 125 in this case. So my final temp is 125. I started at 100, and now this time it is steam or vapor. So it's 2.0 joules per gram Celsius. So then I get all these values. Now it is your decision whether to put it in joules or kilojoules if they did not specify. By adding them all up, you either get 46,148 joules. Usually when you're into the 10,000s of joules, it is usually more appropriate to put it into kilojoules. So it would result as 46.1 kilojoules of energy needed to be absorbed to go from ice to steam at those temperatures and that amount.